Hello, everyone. Welcome to Sleep Space. Tonight, we will talk about what they didn't teach you about Saturn. Whether you're here to learn something new or simply drift into restful sleep, this journey through space will be calm, gentle, and filled with wonder. Now, let's begin with the story of one of the most majestic planets in our solar system, Saturn, the sixth planet from the Sun. A gas giant wrapped in an elegant set of rings that has fascinated observers for centuries. But how did this world come to be? To answer that, we have to go all the way back, billions of years, to the formation of our solar system. Roughly 4.6 billion years ago, a massive cloud of gas and dust, known as the solar nebula, began to collapse under its own gravity. As it condensed, it spun faster and flattened into a disk. At the center of this disk, the sun ignited. Around it, particles of dust and ice began to stick together. These small grains formed clumps. The clumps grew into rocks. The rocks collided, forming even larger bodies called planetesimals. In the outer regions of the solar nebula, where temperatures were low enough for ice to remain solid, these planetesimals had access to far more building material than their rocky cousins closer to the sun. This allowed a few of them to grow into massive cores, 10 or more times the size of Earth. These cores had enough gravity to pull in vast envelopes of hydrogen and helium, becoming gas giants. Saturn was one of them. It's believed that Saturn's core formed within a few million years after the birth of the Sun, swiftly gathering gas before the solar wind blew away the remaining hydrogen and helium from the solar nebula. Saturn ended up with a core of rock and ice, surrounded by layers upon layers of gas, mostly hydrogen, with some helium and traces of other elements. As Saturn grew, it became a dominant force in the outer solar system. Its gravity sculpted the space around it, influencing the formation of moons and shaping the dynamics of the Kuiper Belt and asteroid populations. Some scientists believe Saturn may have migrated slightly from its original orbit, its movement subtly affecting the orbits of other growing planets. While Earth and the inner rocky worlds were still dealing with collisions from leftover debris, Saturn settled into a colder, quieter part of the solar system. But it wasn't alone. Dozens of small, icy objects were caught in its orbit. Some were captured by its gravity. Others formed from the disk of gas and dust that surrounded Saturn during its final stages of formation. These objects became Saturn's moons, companions in orbit. Titan, the largest of them, would go on to become a world of its own, with rivers, lakes, and even rain, made not of water, but of methane and ethane. For a long time, Saturn remained unknown to humanity. But about 4,000 years ago, ancient astronomers began to notice its soft glow in the night sky. To the Babylonians, it was a god. To the Greeks, it was Kronos, father of Zeus. The Romans called it Saturnus, the god of agriculture and time. Unlike stars, Saturn moved against the background of the night sky. It was one of the 5 visible planets known to ancient civilizations. Saturn didn't twinkle. It glowed with a steady light, golden and mysterious. Through the centuries, it inspired myths, calendars, and beliefs. But it was still just a point of light, until one man changed everything. In 1610, Galileo Galilei turned his newly built telescope towards Saturn. What he saw was confusing. He thought Saturn had 2 large moons on either side. A few years later, he wrote that Saturn had ears. His telescope was too weak to show the full picture. But he knew something was different about this planet. In 1655, Dutch astronomer Christiaan Huygens used a more powerful telescope and discovered the truth. Saturn was surrounded by a ring. Or so he thought. Later, astronomers revealed that Saturn didn't have just one ring, but many, and they weren't solid. They were made of countless particles, tiny icy rocks and dust, each orbiting Saturn independently, like a vast, thin, shimmering disk. These rings became Saturn's signature. They extend over 280,000 kilometers from the planet's center, yet are often no more than 10 to 30 meters thick. If you stood inside the rings, they would appear more like a vast, glittering field of ice than a solid wall. They reflect sunlight brilliantly, which is why Saturn is so bright in our skies. But Saturn is more than its rings. It's a giant, dynamic planet with powerful winds, swirling storms, and a magnetic field. Saturn spins rapidly, completing a full rotation every 10.7 hours, making it the second fastest spinning planet in the solar system after Jupiter. This fast spin, combined with its gaseous nature, flattens Saturn at the poles and bulges it at the equator. Looking deeper, Saturn's atmosphere is made mostly of hydrogen, about 96%, with helium making up most of the rest. There's also trace amounts of methane, ammonia, and other gases that give Saturn its pale, golden hue. High in the clouds, ammonia ice forms white bands and zones, similar to Jupiter's but more muted. Beneath that lies water ice and ammonium hydrosulfide. Saturn is known for its storms. Though less colourful than Jupiter's Great Red Spot, Saturn has its own giant tempests. Once every 30 years, a massive storm breaks out, called the Great White Spot. It encircles the planet, creating brilliant white clouds visible even from Earth with a small telescope. These storms are driven by heat rising from Saturn's deep interior, as the planet continues to radiate more energy than it receives from the Sun. Beneath the atmosphere lies a thick layer of metallic hydrogen, a state of matter formed under immense pressure, where hydrogen behaves like a metal and conducts electricity. Deeper still may be a rocky core, 10 to 20 times the mass of Earth, surrounded by layers of ice and gas compressed by gravity. One of Saturn's most unique features is its hexagonal storm at the North Pole. This strange, six-sided jet stream was first photographed by the Voyager spacecraft and later explored in detail by Cassini. The hexagon is about 30,000 kilometers across, larger than Earth, and it rotates with the planet. No other planet has anything quite like it. Scientists believe it's caused by differences in wind speed at different latitudes, creating standing waves in the atmosphere. Speaking of exploration, much of what we know about Saturn today comes from robotic missions. The first spacecraft to fly by was Pioneer 11 in 1979. It gave us our first close-up look. Then came Voyager 1 and Voyager 2 in the early 1980s, which provided breathtaking images and revealed new moons and details about the rings. But it was the Cassini-Huygens mission that truly changed our understanding of Saturn. Launched in 1997, it arrived in 2004 and spent 13 years orbiting the planet. Cassini sent back over 400,000 images, mapped the rings in exquisite detail, discovered geysers on the moon Enceladus, and delivered the Huygens probe to Titan's surface, making it the first and only landing on a body in the outer solar system. Cassini's mission ended in 2017 with a dramatic plunge into Saturn's atmosphere, ensuring it wouldn't contaminate any of the potentially habitable moons. During its final descent, Cassini continued to transmit data until the very last moment, falling into Saturn like a final whisper. Today, Saturn remains a subject of fascination. It is home to at least 145 confirmed moons, more than any other planet. These range from tiny ice balls only a few kilometers wide to Titan, which is larger than Mercury. Some moons are geologically active, others are frozen and ancient. Enceladus, in particular, has become a prime candidate in the search for extraterrestrial life due to the discovery of a global subsurface ocean beneath its icy crust. Saturn's gravity also affects the solar system in more subtle ways. Its mass helps protect Earth from some comets and asteroids, and its orbit may influence long-term climate patterns on our planet. It is both a shield and a mystery, a giant world still revealing its secrets. From its ancient formation to modern exploration, Saturn represents one of the most beautiful and complex objects in our solar system. Its story is the story of our solar system, the story of dust and gas becoming planets, of order emerging from chaos, and of humans reaching out across space to understand it all. And so we end this first chapter with Saturn rising in the twilight sky, its golden glow reminding us of how much there is to discover and how far we've already come. As we continue our journey through Saturn's rich and mysterious history, we turn our attention to its remarkable rings, perhaps the most iconic feature in the solar system. Though Saturn itself is a gas giant with no solid surface, its rings create the illusion of something ornate and structured, like a jeweled crown around a planet of wind and storm. The rings of Saturn have fascinated humanity for centuries, but their true nature remained a mystery until the era of telescopic observation and space exploration. What we now know is that Saturn's rings are not solid structures, but rather massive, flat systems made up of billions, possibly trillions of individual particles. These particles range in size from microscopic grains to boulders as large as houses, and are composed primarily of water ice, with smaller amounts of rock and dust. There are 7 main rings, labelled A through G, with many smaller ringlets and divisions between them. The brightest and most visible of these are the A, B, and C rings. The Cassini division, a dark gap between the A and B rings, is one of the most prominent features visible through a backyard telescope. It's not actually empty, just a region with fewer particles caused by gravitational interactions with Saturn's moon Mimas. Despite their vast width, stretching out more than 280,000 kilometers from Saturn's center, the rings are incredibly thin, sometimes only tens of meters thick. If Saturn were the size of a basketball, the rings would be thinner than a sheet of paper. This delicate, almost two-dimensional structure makes them unique in the cosmos. But where did Saturn's rings come from? Scientists once believed the rings formed alongside Saturn, as leftover debris from the planet's formation. However, recent evidence suggests they may be much younger, perhaps only 100 to 200 million years old. This would mean that when dinosaurs roamed the Earth, Saturn may not yet have had its famous rings. One leading theory is that the rings were born from a moon that got too close to Saturn. According to this idea, a large icy moon, possibly a Titan-sized object, drifted within Saturn's Roche limit, the point at which the planet's gravity becomes so strong that it can tear apart anything held together by its own gravity. Once the moon crossed this boundary, Saturn's immense tidal forces ripped it apart. The shattered remains spread into orbit, forming the icy ring system we see today. Another possibility is that a comet, or series of comets, collided with one or more of Saturn's moons, ejecting ice and dust into space. These materials then became trapped in Saturn's orbit, gradually spreading out into rings. Still, the exact origin of the rings remains uncertain. What we do know is that they are constantly changing. Small moonlets within the rings create waves, bends, and gaps. acting like shepherds that guide and shape the particles around them. These tiny moons keep the ring structure stable and prevent particles from drifting apart. The most famous of these ring shepherds are Pan and Daphnis, which orbit within the narrow Encke and Keeler gaps, respectively. Their gravity carves out clean paths in the rings, and their motion generates beautiful spiral waves, ripples that slowly spread through the ring material like the wake of a boat through water. Observations from the Cassini spacecraft revealed even more wonders. In the B ring, scientists discovered mysterious vertical structures rising more than 2 kilometers above the ring plane, much taller than the average thickness of the rings themselves. These features may be caused by the gravitational pull of small, unseen moonlets, and they cast long shadows when the sun strikes the rings at a shallow angle. Then there are the spokes. These are ghostly, radial features that appear and disappear mysteriously in the rings, especially in the B ring. First seen by Voyager, they look like shadows or smudges, rotating with the rings. The cause is still debated, but many scientists believe they are electrostatically charged dust particles lifted slightly above the ring plane by Saturn's magnetic field. Speaking of magnetism, Saturn has a powerful magnetic field, though not as strong as Jupiter's. What makes Saturn's magnetic field unusual is that it is nearly perfectly aligned with the planet's rotation axis, something that defies our current understanding of planetary magnetic fields. This alignment makes it difficult to determine exactly how fast Saturn rotates at its core, as the usual method, tracking the wobble of the magnetic field, doesn't work here. Saturn's magnetic field is generated deep within the planet, likely by the motion of metallic hydrogen in its interior. The field extends far into space, creating a magnetosphere that traps charged particles and protects the planet from solar radiation. This magnetosphere also interacts with the rings and moons, influencing their structure and behavior in subtle but important ways. Beyond the rings, Saturn's family of moons continues to astound scientists and spark the imagination. With over 145 confirmed moons, Saturn holds the record for the most satellites of any planet in the solar system. These moons vary widely in size, composition, and geological activity, offering a diverse array of worlds to study. The largest of these is Titan, a moon so large it's bigger than the planet Mercury. Titan has a thick, nitrogen-rich atmosphere, denser than Earth's, and a complex weather system that includes clouds, rain, rivers, lakes, and seas. But unlike Earth, Titan's weather is based on methane, not water. Methane falls as rain, carves channels in the surface, and collects in vast lakes near the poles. Underneath Titan's icy crust lies a salty, global subsurface ocean. This makes Titan not just interesting, it makes it a prime candidate in the search for extraterrestrial life. Organic molecules are abundant in its atmosphere, and the conditions might be suitable for microbial life, either in the ocean below or in some other exotic form we don't yet understand. Titan isn't alone in its intrigue. Enceladus, a much smaller moon, stunned scientists when Cassini discovered geysers of water vapor and ice erupting from its south pole. These plumes shoot hundreds of kilometers into space and contain water, salts, organic molecules, and even hints of hydrothermal activity on the ocean floor. The source of these geysers is a global subsurface ocean beneath Enceladus's icy shell. Heat from tidal flexing, caused by Saturn's gravity pulling and stretching the moon, keeps the ocean liquid despite the frigid surface temperatures. The presence of heat, water, and organic chemistry makes Enceladus another prime target in the search for life beyond Earth. In fact, Cassini flew directly through one of these plumes, sampling the material and sending the data back to Earth. What it found was astonishing: evidence of complex organic compounds, indicating that Enceladus might have the ingredients for life. Some scientists now dream of a future mission that could land near one of the geysers, or even dive into the ocean below. Other moons of Saturn include Iapetus, which has one hemisphere as bright as snow and the other as dark as coal. This dramatic contrast is caused by a combination of dust from other moons and the sublimation of ice. Iapetus also has a strange equatorial ridge, making it resemble a walnut. There's also Mimas, a small, heavily cratered moon that resembles the Death Star from Star Wars, thanks to the enormous Herschel crater that dominates its surface. And Tethys, which features a massive canyon system called Ithaca Chasma, stretching over 2,000 kilometers long. Each of Saturn's moons tells a story of formation, of collision, of ice and time. Some are ancient relics, unchanged for billions of years. Others are geologically active, reshaping themselves even now. Together, they form a miniature solar system within Saturn's gravitational embrace. The diversity of Saturn's moons has led scientists to reconsider what moons can be. No longer just passive rocks orbiting planets. Many are dynamic, complex worlds in their own right. They have mountains, canyons, volcanoes, some of them icy, and possibly even life-supporting environments. This complex system, rings, moons, magnetic fields, and storms, makes Saturn one of the most scientifically rich and visually stunning objects in the solar system. And yet, we've only just begun to understand it. Though Cassini's mission is over, Saturn continues to hold mysteries waiting to be uncovered. Future missions are in development, including NASA's Dragonfly, which is scheduled to launch in the 2030s. Dragonfly is a drone-like rotorcraft that will fly through Titan's thick atmosphere, exploring multiple locations and analyzing surface chemistry in search of the building blocks of life. As technology improves, we'll be able to send more advanced instruments, orbiters, and maybe even landers to the moons of Saturn. We'll peer beneath icy shells, swim through alien oceans, and uncover the processes that make these moons active and possibly habitable. But even as we plan for the future, the legacy of Saturn's exploration reminds us how far we've come. From Galileo's sketch of Ears to Cassini's final descent into the clouds, Saturn has taught us about planetary formation, the complexity of ring systems, the potential for life beyond Earth, and the sheer beauty of the cosmos. In the next chapter, we'll dive deeper into the physics of Saturn itself, how its gravity works, the nature of its internal heat, and how it interacts with its surroundings in ways that are still being studied. For now, just imagine Saturn as it is, hanging in the darkness of space, wrapped in its shimmering rings, surrounded by an entourage of moons, each one a world of its own. It is a planet of elegance and extremes, mystery and majesty. Now that we've explored Saturn's internal structure, rings, and atmospheric dynamics, we turn our attention to the planet's extraordinary collection of moons. With over 145 confirmed satellites, Saturn holds more natural moons than any other planet in the solar system. These moons are not mere lumps of rock and ice orbiting a giant. Many are complex, dynamic worlds with rich geologic histories, and some may even harbour life. Let us begin with the most famous and perhaps the most intriguing: Titan. Titan is Saturn's largest moon and the second largest moon in the solar system, just slightly smaller than Jupiter's Ganymede. At 5,150 kilometers across, Titan is even bigger than the planet Mercury. But what makes Titan truly special isn't just its size, it's its atmosphere. Titan has a dense, nitrogen-rich atmosphere that is thicker than Earth's. It's the only moon in the solar system with a significant atmosphere, and it's the only known body other than Earth to have stable liquids on its surface. But instead of water, Titan's rivers, lakes, and seas are made of liquid methane and ethane. The surface temperature on Titan is around minus 179 degrees Celsius, or minus 290 degrees Fahrenheit, cold enough for methane to behave like water does on Earth, forming clouds, causing rain, and filling vast seas. This methane cycle mirrors Earth's hydrological cycle in remarkable ways. There are methane clouds in the sky, occasional methane rainstorms, and even deltas where rivers feed into lakes. In fact, some of Titan's lakes are huge. The largest, Krakenmare, spans over 1,000 kilometers. These dark, hydrocarbon-rich bodies of liquid are not only fascinating, they're potentially habitable, at least in the sense of supporting some exotic form of life adapted to extreme conditions. Underneath this alien landscape, scientists believe a global subsurface ocean of liquid water exists, likely mixed with ammonia, which lowers the freezing point. The presence of both a stable surface environment and a hidden ocean makes Titan a compelling destination in the search for life. In 2005, the European Space Agency's Huygens probe, carried by NASA's Cassini spacecraft, descended through Titan's thick orange atmosphere and landed on its surface. It was the first and only landing ever achieved in the outer solar system. Huygens sent back photos of pebbles made of water ice and recorded a sky dimly lit by the sun through a haze of organic molecules. The success of Huygens opened the door for further exploration. In the coming decades, NASA plans to launch Dragonfly, a rotorcraft mission to Titan. This flying laboratory will be able to travel from one location to another, sampling the chemistry of different regions and searching for prebiotic conditions. Dragonfly is set to revolutionize our understanding of Titan and maybe even life itself. But Titan isn't Saturn's only mysterious moon. Let's travel now to Enceladus. Tiny Enceladus, only about 500 kilometers in diameter, would be easy to overlook if it weren't for one stunning discovery. It's actively spraying water from its south pole. These geysers erupt through fractures known as tiger stripes, long, warm fissures in the icy crust. The material from the geysers forms a giant plume that extends hundreds of kilometers into space and contributes to Saturn's E-ring. When Cassini flew through the plume, it sampled the contents directly. The findings were extraordinary. Water vapor, salts, simple and complex organic molecules, silica grains, and even signs of hydrothermal activity. This suggests that beneath Enceladus's frozen surface is a liquid ocean, kept warm by tidal heating, generated as the moon flexes under Saturn's gravity. The presence of heat, liquid water, and organics makes Enceladus one of the most promising places in the solar system to look for microbial life. In fact, some scientists believe that if life is ever found beyond Earth, Enceladus could be the first place we find it. Despite its small size, Enceladus is a geologically active world with a subsurface ocean, possibly in contact with a rocky core, an environment similar to hydrothermal vents on Earth, where life may have first emerged. The revelations from Enceladus have reshaped our ideas about habitability. It turns out that moons, especially icy ones, can be just as promising as planets in the search for life. Let's now venture outward to one of Saturn's strangest moons, Iapetus. Iapetus is unique in many ways. It's tidally locked, like most moons, which means the same side always faces Saturn. But its leading hemisphere, the side facing forward in its orbit, is extremely dark, while the trailing side is bright. This creates a dramatic two-tone appearance, unlike anything else in the solar system. The dark side is covered in a layer of material that may have originated from another moon, Phoebe, and migrated inward. This dark coating absorbs heat, which then causes more ice to sublimate, reinforcing the contrast in a runaway effect. Another strange feature of Iapetus is its equatorial ridge, a massive mountain range that runs like a belt around the moon's equator, giving it a walnut-like appearance. The origin of this ridge remains uncertain. It may be the remnants of an ancient ring that collapsed onto the surface, or perhaps the result of tectonic forces from a rapidly spinning past. Moving closer to Saturn, we encounter Mimas, a small, heavily cratered moon with a striking resemblance to the Death Star from Star Wars. This comparison comes from the Herschel crater, a colossal impact site that covers nearly a third of the moon's diameter. Despite its scarred appearance, Mimas may also harbour a subsurface ocean, although the evidence is still debated. Variations in its rotation suggest an internal complexity that belies its frozen, static exterior. Then there's Tethys, a medium-sized moon known for its own massive scar, Ithaca Chasma, a canyon stretching over 2,000 kilometers long, roughly 3/4 the circumference of the moon. Tethys is mostly composed of water ice and has a low density, suggesting a largely undifferentiated interior. Its surface is heavily cratered, including the enormous Odysseus crater, which, like Herschel on Mimas, hints at a violent history. Another of Saturn's more interesting moons is Dione, which is about 1,120 kilometers in diameter. Dione's surface also shows signs of tectonic activity, including long, bright ice cliffs known as wispy terrain. These features are not just surface coloration, they are actual, steep cliffs created by tectonic fractures. Dione too might have a subsurface ocean. Gravity measurements from Cassini hint at a possible global layer of water beneath its icy crust. If confirmed, this would add yet another potentially habitable moon to Saturn's collection. Next, we come to Rhea, Saturn's second largest moon. Rhea is an icy world with a heavily cratered surface and no known geological activity. However, one of the most fascinating aspects of Rhea is the evidence for thin rings or debris clouds in orbit around it, a rare feature for a moon. If confirmed, Rhea would be the only known moon with rings. There are also dozens of small, irregular moons orbiting Saturn, some of which were likely captured from the Kuiper belt or asteroid belt. These include Hyperion, a chaotic, tumbling sponge of a moon with extremely low density and strange, porous features, and Phoebe, which orbits Saturn backward in a retrograde path and is believed to be a captured object from the outer solar system. Together, Saturn's moons create a vast and diverse system, each body contributing a unique chapter to the story. Some moons are ancient relics, preserving the solar system's early history. Others are geologically active, reshaping themselves even now. And a few may offer the right conditions for life, as we don't yet know it. The sheer number of moons and the diversity among them suggest that Saturn's gravitational reach has been sculpting and capturing celestial bodies for billions of years. This dynamic system also provides natural laboratories for studying everything from geophysics to astrobiology. Saturn's moons aren't just scientifically important, they're visually spectacular. Each flyby by the Cassini spacecraft revealed incredible vistas: icy cliffs, cratered plains, frozen oceans, and alien skies. These images captured the imagination of scientists and the public alike, reminding us of the beauty and variety of the outer solar system. Looking ahead, future missions may aim to revisit these moons with landers, orbiters, and possibly sample return spacecraft. Enceladus and Titan are at the top of the list, given their potential for habitability. But even the smaller moons hold secrets worth uncovering: evidence of past collisions, clues about Saturn's early history, and perhaps even building blocks of life. The study of Saturn's moons teaches us something profound: that worlds capable of wonder, beauty, and mystery don't need to be planets. In the shadow of a giant, in the cold outer reaches of the solar system, lie places that challenge our ideas of where life can exist and what planetary systems can look like. As we leave these moons behind for now, remember that each one is a world unto itself. Some are frozen and quiet, others erupt with life-giving water. All of them orbit the ringed giant in a celestial dance that has lasted for billions of years and will likely continue for billions more. We now return our focus to the spectacular and delicate architecture of Saturn's rings. Not just their structure or composition, but the hidden forces that govern them. From gravitational interactions to electromagnetic influences, Saturn's rings are not only beautiful but dynamic, responsive systems that behave more like living, breathing entities than simple, frozen debris fields. We often think of rings as static and unchanging, but the truth is that Saturn's rings are in constant motion. Every particle, whether a grain of dust or a house-sized boulder, follows its own orbit around the planet, obeying the laws of physics with extraordinary precision. And yet, these countless particles are not moving in isolation. They are part of a massive, interconnected structure that is shaped by gravity, resonances, collisions, and even light. To understand the nature of Saturn's rings, we must first grasp the idea of orbital resonance. This concept is at the heart of many of the features we see in the rings, from gaps to edges to spiraling waves. Orbital resonance occurs when the orbital period of one body is a simple ratio of another's. For example, when a ring particle orbits Saturn twice for every single orbit of a moon. When such a resonance exists, the gravitational influence of the moon tugs on the ring particles at the same location in each orbit, like pushing a child on a swing. Over time, this repeated gravitational nudge builds up, creating gaps, waves, or even pushing particles out of certain regions altogether. The Cassini division, the most famous gap in Saturn's rings, is one of the clearest examples of this. It's maintained by a 2-1 resonance with Saturn's moon Mimas. Any particle that tries to orbit in this region is repeatedly disturbed by Mimas's gravity, eventually getting moved to a different, more stable orbit. The result is a relatively empty space that carves a sharp line between the A and B rings. But resonances do more than create gaps. They also form waves. These can be either density waves, where the number of particles increases and decreases along a spiral, or bending waves, where the ring plane itself is tilted slightly up and down. These spiral patterns travel through the rings like ripples in water, revealing the subtle pull of Saturn's moons, and even the oscillations within Saturn itself. The presence of these waves has turned the rings into a kind of seismograph. By analysing their frequencies and shapes, scientists can infer what's happening inside Saturn, such as how its mass is distributed or how its interior vibrates. This technique, known as ring seismology, offers a way to study the planet's interior without having to go beneath its cloud tops. Another factor that influences ring dynamics is shepherd moons, small moons that orbit close to the edges of the rings and help maintain their structure. These moons use their gravity to push particles back into place, confining the rings to narrow, sharp-edged bands. For example, the A ring is bounded by two shepherd moons, Prometheus on the inside and Pandora on the outside. Their constant gravitational interactions create beautiful scalloped patterns along the ring edge, as if the ring were breathing in and out with each orbit. Inside the rings, some of the most intricate and stunning effects are caused by moonlets, small, often undetectable objects that stir up the ring particles around them. One of the most visually striking examples is Daphnis, a tiny moon only about 8 kilometers wide, which orbits within the Keeler gap of the A ring. As it moves through the gap, its gravity pulls on the ring particles nearby, creating vertical waves that ripple above and below the ring plane like frozen waves in time. These features highlight a key characteristic of the rings: their thinness. Despite their vast width, the rings are only about 10 to 30 meters thick on average. This means that vertical disturbances, even a few kilometers high, stand out dramatically. From space, these patterns look like sculpted lines on a record, etched by the constant motion of gravity and time. Another curious phenomenon seen in the rings is the appearance of spokes, transient, ghostly lines that seem to move radially across the rings. First seen by the Voyager spacecraft in the 1980s, spokes were long a mystery. Unlike the rest of the ring particles, which orbit Saturn rapidly, the spokes appear to hover, rotating more slowly and independently. Today, scientists believe these spokes are caused by electrostatic charges. When tiny ring particles are hit by ultraviolet light from the sun or by micrometeorites, they can become electrically charged. These charged particles are then influenced by Saturn's magnetic field, causing them to lift slightly above the ring plane and align in distinct patterns. Saturn's magnetic field plays a much larger role in the ring system than one might expect. Like Earth and Jupiter, Saturn generates a magnetic field through the motion of metallic hydrogen deep in its interior. But Saturn's field is unusual in that it's nearly perfectly aligned with its rotational axis. This symmetry defies existing models of planetary magnetic dynamos and remains a subject of ongoing research. The magnetic field creates a magnetosphere, a vast region of space dominated by Saturn's magnetic influence. Within this zone, charged particles spiral along magnetic field lines, and interactions with the solar wind create auroras near the poles. Unlike Earth's visible auroras, Saturn's glow primarily in ultraviolet, but they are just as dynamic, pulsing and shifting as particles stream into the atmosphere. The magnetosphere also affects the rings. As charged dust particles within the rings interact with Saturn's magnetic field, they become part of a complex plasma environment. In fact, the ring rain phenomenon, where material from the rings slowly drifts down into the planet's atmosphere, is at least partly driven by these electromagnetic forces. This ring rain consists of water ice particles, dust, and organic compounds that fall along magnetic field lines into Saturn's upper atmosphere. Over time, this process is gradually depleting the rings. Measurements from the Cassini spacecraft estimate that Saturn is losing up to 10 tons of ring material per second, a slow but continuous drain that suggests the rings are temporary features on cosmic timescales. Estimates vary, but it's possible that Saturn's current ring system formed only 100 to 200 million years ago, and may disappear within the next 100 million years. That means we live in a special window of time, a fleeting moment when Saturn's rings are visible in all their glory. In the grand arc of the planet's 4.6 billion year existence, the rings may be just a short-lived phenomenon. What then caused the rings to form? One leading theory is that a large icy moon, perhaps as big as Titan, once strayed too close to Saturn and was pulled apart by tidal forces. When a moon enters a region called the Roche limit, the planet's gravity becomes stronger than the moon's own gravity, causing it to disintegrate. The remnants of such a moon could have spread out into the thin, icy disk we now see as rings. Another theory suggests that a series of collisions between moons, comets, or asteroids may have produced enough debris to form the rings. These impacts would have to occur close to the planet, where the material couldn't easily coalesce into another moon, and would instead spread out into a disk. Regardless of their origin, the purity of Saturn's rings is telling. The rings are composed almost entirely of water ice, more than 90% pure in many places. This suggests that they are relatively young, because over billions of years, micrometeorites would have polluted the rings with dark material. The fact that they remain so bright and clean points to a more recent creation. Yet even in their youth, the rings reveal signs of complexity. Cassini discovered propeller-shaped features in the A-ring, evidence of moonlets too small to clear a full gap, but large enough to disturb the particles around them. These features hint at the process of moon formation within the rings themselves. In fact, it's believed that some of Saturn's moons may have formed from the rings. As particles clump together over time, they can grow into larger bodies, potentially becoming new moons in a process known as accretion. This cycle of destruction and rebirth, where moons are broken apart to form rings and rings give birth to new moons, is part of Saturn's ongoing evolution. This concept is especially vivid when we look at moons like Pan and Atlas, which orbit within the rings and have strange, flying saucer-like shapes. These unusual forms are likely the result of slow accretion from ring material, piling up equatorial ridges of ice and dust over eons. In many ways, Saturn's rings are like a celestial laboratory, showing us the processes of planetary formation in miniature. The interactions we observe, resonances, accretion, erosion, heating, charging, mirror the same physical principles that shaped the solar system billions of years ago. And all of it, this delicate balance of icy particles, moonlets, and electromagnetic forces, depends on the vast, invisible hand of Saturn's gravity. It is gravity that binds the rings, sculpts the moons, stirs the atmosphere, and pulls meteors from the sky. It is gravity that maintains the grand clockwork of Saturn's system. Saturn, in this sense, is not just a planet, it is a system unto itself. A central body surrounded by dozens of moons, thousands of ringlets, and trillions of particles. It is a dynamic environment, full of collisions, orbits, chemistry, and change. And all of it moves to the rhythm set by Saturn's mass and motion. As we drift through this magnificent region of space in thought, we begin to appreciate the elegance of the entire system. The rings are more than decoration. They are active, responsive, and meaningful. They record the past, influence the present, and may hint at Saturn's future. To understand Saturn fully, we must go back, far back, to the earliest days of the solar system. Around 4.6 billion years ago, our sun was still forming within a vast cloud of gas and dust. That cloud, known as the solar nebula, eventually collapsed under its own gravity, igniting nuclear fusion at the core and giving birth to our star. But the story didn't end with the sun. Surrounding this newborn star was a swirling disk of leftover material, still dense with hydrogen, helium, and trace elements formed in earlier generations of stars. This protoplanetary disk was where the planets, moons, and smaller bodies of the solar system would eventually emerge. Close to the Sun, only rocky materials could condense due to the high temperatures. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small and rocky. Farther out, however, temperatures were low enough for ices and gases to condense. This region, beyond what's called the frost line, was fertile ground for the formation of gas giants. Here, in this cold outer domain, Saturn began to form. The leading theory for the formation of gas giants is the core accretion model. According to this model, tiny bits of rock and ice clump together over time, forming larger and larger planetesimals. Eventually, some of these grew massive enough, about 10 Earth masses, to begin pulling in gas from the surrounding disk. Saturn's rocky core likely formed first, gathering icy material and debris until it became large enough to exert a strong gravitational pull. Once it passed a critical threshold, it began rapidly accreting hydrogen and helium, the most abundant elements in the nebula. This gas collapse happened quickly, over the course of just a few million years, before the solar wind from the young sun swept away the remaining gas. Saturn was not alone in this process. Jupiter formed slightly earlier and became even more massive. Together, these two giants shaped the architecture of the outer solar system. Their immense gravity influenced the orbits of nearby planetesimals, disrupted growing planetary embryos, and helped define the boundaries between the terrestrial and gas giant worlds. Saturn's role in the solar system's development was more than just passive. Some models suggest that Jupiter and Saturn once migrated inward toward the Sun, only to reverse direction in a dramatic event known as the Grand Tack hypothesis. According to this theory, Jupiter began spiraling inward, dragging debris with it, but was halted by Saturn's formation. Their mutual gravitational resonance caused both giants to migrate back outward, reshaping the disk of material and limiting the size of Mars. This planetary migration had ripple effects. It scattered asteroids, carved out gaps in the disk, and may have delivered water-rich bodies to Earth. In this way, Saturn may have played a key role in the development of a habitable planet, our own. Another hypothesis, known as the Nice model, named after the city in France where it was developed, suggests that about 500 million years after their formation, the gas giants, including Saturn, underwent a chaotic reshuffling of orbits. This event may have led to the Late Heavy Bombardment, a period of intense impacts across the solar system. Saturn, once again, was a central player, with its gravity helping to destabilize small icy bodies and fling them into the inner solar system. This chaotic history shaped not only the planets, but also the populations of moons and rings. Moons were captured, others destroyed. Debris fields became rings or seeded new moons. It was a time of immense change, and Saturn's gravity was one of the dominant forces driving it. As the solar system stabilized, Saturn settled into its current position, roughly 1.4 billion kilometers from the Sun. From this distance, it takes about 29.5 Earth years for Saturn to complete a single orbit. Its vast reach and powerful gravity continued to influence the space around it, collecting an entourage of moons, many of which formed from the same material that built Saturn itself. But not all of Saturn's moons were formed in place. Some were likely captured objects, planetesimals that wandered too close and became gravitationally bound. This is particularly evident with irregular moons like Phoebe, which orbits Saturn in a retrograde direction, opposite the planet's rotation. Phoebe's composition also differs from Saturn's inner moons. suggesting it may have originated in the Kuiper belt, far beyond Neptune. In this way, Saturn serves as a cosmic archive, preserving material from distant regions of the solar system. By studying its captured moons, scientists gain insight into places we've never visited, tiny frozen relics of the solar system's outer reaches. Saturn also acts as a gravitational gatekeeper. Its immense mass deflects or captures many incoming objects, asteroids, comets, and stray icy bodies that might otherwise threaten the inner planets. In this protective role, Saturn has reduced the number of major impacts on Earth and its neighbours, increasing the stability of the inner solar system. Saturn's magnetosphere, generated by the movement of metallic hydrogen deep within its core, further adds to its cosmic influence. This invisible shield extends millions of kilometers into space, creating a protective bubble around the planet and its moons. It traps charged particles from the solar wind and produces spectacular auroras near Saturn's poles. Though invisible to the naked eye, these auroras light up in ultraviolet, pulsing with the rhythm of the planet's magnetic field. The magnetosphere also interacts directly with the rings and the moons. For instance, the icy plumes from Enceladus contribute material to Saturn's E-ring, which in turn feeds the magnetosphere with water vapor and other ions. This creates a unique feedback system where a moon fuels a ring and the ring charges the magnetosphere, all orbiting the same giant planet. Over the course of billions of years, this system has evolved into a dynamic, interlinked structure, one that is far more than the sum of its parts. Saturn isn't just a planet with rings and moons. It is a gravitational system, a magnetic engine, a chemical laboratory, and perhaps in places, a cradle for life. Even Saturn's tilt, about 26.7 degrees, similar to Earth's, may be the result of gravitational interactions with Neptune. This axial tilt gives Saturn seasons, just as Earth experiences. But since Saturn's orbit takes nearly 30 Earth years to complete, each season lasts over 7 Earth years. This slow cycle influences everything from cloud formation to ring illumination, providing natural variations that scientists can observe and model over decades. The changing angle of the rings as Saturn moves through its orbit is one of the most spectacular visual events in planetary science. From Earth, the rings sometimes appear fully open, tilted at 27 degrees, offering a grand, glittering spectacle. At other times, they are nearly edge-on and can disappear entirely from view in small telescopes. This phenomenon occurs roughly every 15 years and offers a periodic reminder of the complexity of Saturn's orbit and the three-dimensional nature of space. Through it all, Saturn remains a planet of contrast. It is at once ancient and dynamic, massive and delicate, violent and serene. Its storms rage for decades, but its rings are nearly silent. Its core may be dense rock and ice, yet it floats in water. Its influence stretches far across the solar system, yet its own fate may be sealed by tiny particles drifting into its clouds. And so Saturn, while one of the most majestic sights in the sky, is not eternal. Its rings will fade, its moons may shift, its atmosphere will continue to change. But its role in the solar system's history is secure. It helped shape the early planets, protected the inner system, and now serves as a gateway to some of the most compelling science in the cosmos. Saturn is, in many ways, a storyteller. Its rings tell of shattered moons. Its moons speak of hidden oceans and ancient captures. Its storms record the power of convection and chemistry. Its very presence, Immense, luminous, and always in motion, tells the story of a solar system born in chaos, yet capable of such intricate order. The story of Saturn is not just a tale of distant moons and rings, it is also the story of human curiosity. From the earliest telescopic glimpses to the grand modern spacecraft that orbited the planet for over a decade, Saturn has beckoned observers for centuries with its mysterious beauty. In this part, we explore the history of how we've studied Saturn, and how each step revealed more than we ever expected. Saturn has been visible to the naked eye for as long as humans have looked at the sky. It moves slowly against the stars, shining with a steady golden glow. Ancient civilizations watched it carefully. To the Babylonians, Saturn was the star of Ninurta. The Romans named it after their god of agriculture and time. And across cultures, it became associated with structure, cycles, and the passage of ages. But it wasn't until 1610 that Saturn truly came into focus, literally, when Galileo Galilei turned his telescope toward the heavens. What he saw was not clearly understood at first. Galileo described Saturn as having ears or being triple-bodied, because the low resolution of his telescope couldn't clearly resolve the rings. It was a puzzle that would remain unresolved for nearly 50 years. Then, in 1655, the Dutch astronomer Christiaan Huygens, using a far superior telescope, correctly hypothesized that Saturn was surrounded by a thin, flat ring. Huygens also discovered Titan, the largest of Saturn's moons, and published his findings in a coded anagram to protect the claim until he was ready to reveal it. In the decades that followed, Giovanni Domenico Cassini discovered more moons: Iapetus, Rhea, Tethys, and Dione, and identified the large division in the rings that now bears his name, the Cassini division. By the 18th and 19th centuries, telescopes had improved enough to map the planet's cloud bands, polar flattening, and more intricate ring structure. Yet even by the mid-20th century, many of Saturn's mysteries remained untouched. It wasn't until the space age that we began to study the planet up close. The first spacecraft to visit Saturn was Pioneer 11, which flew past in 1979. Its close approach revealed Saturn's powerful magnetosphere and detected some new moons, though it could only provide a brief glimpse. Then came Voyager 1 and Voyager 2, which flew by in 1980 and 1981, respectively. These Voyager missions revolutionized our view of the ringed planet. They imaged the rings in unprecedented detail, revealing thousands of smaller ringlets, as well as the strange radial spokes within the B-ring. They studied the atmospheres of Saturn and Titan, providing temperature readings, wind measurements, and a better sense of the planet's composition. Voyager 1 flew within 4,000 kilometers of Titan, but was unable to see the surface due to the thick atmosphere. Even so, the data it collected confirmed that Titan had an atmosphere denser than Earth's and rich in nitrogen and methane, fueling dreams of what might lie beneath. But it was the Cassini-Huygens mission that would become the crown jewel of Saturn exploration. Launched in 1997, Cassini was a joint mission between NASA, the European Space Agency, ESA, and the Italian Space Agency. It carried with it a smaller lander, Huygens, built specifically to descend to the surface of Titan. Cassini arrived at Saturn in 2004 after a 7-year journey that included gravity-assist flybys of Venus, Earth, and Jupiter. Upon arrival, it entered orbit and began what would become a 13-year mission of breathtaking discovery. Cassini's instruments allowed scientists to study Saturn's atmosphere, rings, magnetosphere, and moons in fine detail. It conducted flybys of nearly every major moon, observing surface features, chemical compositions, and gravitational fields. It tracked weather systems in the atmosphere, including the long-lived polar hexagon and gigantic storms that wrapped around the planet. One of the first major surprises was the discovery of geysers erupting from Enceladus. Cassini not only imaged these plumes, but actually flew through them, using onboard spectrometers to analyze the material. The detection of salts, water, methane, and complex organic molecules hinted at a warm, subsurface ocean, possibly in contact with rock, creating an environment ripe for microbial life. Another highlight was Cassini's long-term observation of seasonal changes on Saturn and Titan. Over the course of its mission, Cassini watched Titan's methane clouds shift across latitudes, monitored the changing coloration of Saturn's rings, and tracked the movement of sunlight across both hemispheres. Titan's lakes, seas, and dunes became better understood as Cassini passed by dozens of times, using radar to peer through the haze. Then, in January 2005, the Huygens probe detached from Cassini and plunged through Titan's thick atmosphere. The descent lasted over 2 hours, during which the probe took the first ever photographs of Titan's surface. It revealed a landscape of icy pebbles, river channels, and dark plains. Though Huygens operated for only about 90 minutes after landing, the images and data it returned were historic, showing for the first time the surface of a world with a methane-based hydrological cycle. Meanwhile, Cassini continued its grand tour. It discovered propeller moonlets in the rings, observed the flying saucer-shaped moons Pan and Atlas, and helped confirm that Saturn's rings are relatively young, perhaps no more than a few 100 million years old. Cassini also studied Saturn's auroras, magnetic field, and internal structure using gravity measurements and occultation experiments. It provided deep insight into the planet's rotation rate, though the task proved difficult because Saturn's radio emissions vary over time, unlike Jupiter's, which complicates determining its exact internal spin rate. As its fuel began to run out, the Cassini mission team planned a spectacular ending. In what became known as the grand finale, Cassini executed a series of daring orbits in 2017 that sent it between the planet and its innermost ring, a region never before explored. These final orbits provided some of the most precise data about Saturn's mass distribution, the structure of its magnetic field, and the composition of the rings. They revealed that the rings are actively interacting with the planet and slowly falling inward. On September 15, 2017, Cassini made its final descent into Saturn's atmosphere, burning up like a meteor. This intentional plunge was designed to protect Titan and Enceladus from accidental contamination, in case any hardy Earth microbes had survived on board the spacecraft. Cassini's end was bittersweet, but it left behind a legacy that will guide planetary science for generations. Over 635 gigabytes of data were collected, resulting in thousands of scientific papers and discoveries that continue to unfold today. Future missions to Saturn are now being planned, most notably Dragonfly, a rotorcraft lander that will explore Titan's surface in the 2030s. Unlike a stationary lander, Dragonfly will be able to fly from site to site, analyzing different environments, sampling organic material, and searching for chemical signs of life. There is also growing interest in a return mission to Enceladus, where future spacecraft may fly through the plumes again, or even land near the source, to search directly for biomarkers in the icy spray. Such missions would aim to answer one of the most profound questions of all: is there life beyond Earth? Saturn's importance in this search cannot be overstated. Between the organic-rich skies of Titan and the liquid oceans of Enceladus, Saturn offers two of the most compelling environments for astrobiology anywhere in the solar system. Even beyond the quest for life, Saturn remains a vital target for understanding planetary formation, magnetospheric physics, and ring dynamics. It is a natural laboratory for studying systems in motion, systems not unlike those around exoplanets we are now discovering in distant star systems. As telescopes like the James Webb Space Telescope begin to study exoplanets with rings or giant gaseous atmospheres, our deep understanding of Saturn will serve as a model. The lessons learned here, in our own backyard, will inform our interpretations of other worlds. It's a reminder that exploration is not just about going somewhere, it's about understanding what we see, building models, asking new questions, and reaching further with each generation. As our tools grow more powerful, as our probes venture further, Saturn will always be there, golden, banded, ringed, and turning slowly in the cold deep of space, watching, waiting, calling us back. Saturn's beauty lies in its rings and moons, but its mystery lies deeper, in the swirling gases of its vast atmosphere and the unseen pressures of its dense, hidden core. Understanding Saturn's internal structure is like solving a cosmic puzzle with invisible pieces. Every temperature reading, magnetic fluctuation, and gravity signature offers a small clue to what lies beneath those clouds. Let's begin at the top. Saturn's atmosphere is composed primarily of hydrogen, about 96%, and helium, making up around 3%, with the rest consisting of trace elements like methane, ammonia, water vapor, phosphine, and other hydrocarbons. These gases form broad, colourful bands that wrap around the planet, though Saturn's colours are subtler than Jupiter's due to differences in cloud chemistry and depth. Unlike Earth, Saturn has no solid surface. What we see as a visible boundary is merely the outer layer of clouds. Clouds which mark a gradual transition from gas to liquid with increasing depth. As you descend, the pressure increases dramatically, compressing hydrogen gas until it becomes a dense, metallic fluid. This means that Saturn doesn't have a hard surface to stand on. If you tried to descend into the planet, you'd eventually be crushed by pressure and heated by temperature long before reaching the core. But through indirect measurements, like how the planet's gravity affects passing spacecraft, we can estimate what the interior might be like. At the uppermost layers, Saturn's clouds form distinct strata, based on the temperature and composition of the gases present. The highest clouds are made of ammonia ice, forming the pale yellow and white hues visible from space. Below that are ammonium hydrosulfide clouds, darker in colour, and beneath those, water clouds, much like those on Earth but buried deep under tremendous pressure. Wind speeds in Saturn's upper atmosphere are among the fastest in the solar system. Near the equator, winds can reach over 1,800 kilometers per hour, far exceeding even Jupiter's jet streams. These high-speed winds, combined with Saturn's rapid rotation, one day on Saturn lasts just over 10.7 Earth hours, create bands and vortices that stretch for thousands of kilometers. Saturn's rotation also flattens the planet noticeably. Its equatorial diameter is about 10% larger than the distance from pole to pole. This flattening, called oblateness, is one of the most extreme of any planet in the solar system, and it's a direct consequence of spinning so rapidly while being composed of compressible gas. At the poles, Saturn exhibits unique weather systems, especially at the North Pole, where we find one of the most bizarre features in the entire solar system, the hexagon. Discovered by Voyager and studied in detail by Cassini, the hexagon is a six-sided jet stream that spans over 30,000 kilometers, wider than Earth itself. It rotates with the planet, maintains its shape over decades, and may extend deep into Saturn's atmosphere. No one fully understands how it formed, though it may be the result of fluid dynamics in a rapidly rotating atmosphere. Laboratory simulations on Earth can reproduce hexagonal flows under specific conditions, lending some support to this theory. Saturn's storms can also be colossal. Approximately once every Saturnian year, a 30-year Earth cycle, a massive storm erupts in the northern hemisphere. These great white spots, as they are called, are planet-encircling systems driven by internal heat rising to the surface, igniting convective towers of clouds and lightning. The most recent of these storms occurred in 2010 and was observed by Cassini in extraordinary detail. It spanned over 10,000 kilometers in width, produced thunder and lightning, and altered the atmosphere's temperature and composition for years. In these moments, Saturn's calm exterior erupts into chaos, briefly revealing the powerful energies at work below. Deeper still, Saturn's internal structure is layered like an onion. Beneath the clouds, the pressure increases rapidly. Hydrogen, being the dominant element, begins to behave in unusual ways under compression. At around 1.4 million kilometers below the cloud tops, hydrogen becomes a liquid metal, a phase not found naturally on Earth, but common in the interiors of gas giants. Metallic hydrogen conducts electricity, and this is likely where Saturn's magnetic field is generated. Unlike Earth's dynamo, which operates in a molten iron core, Saturn's dynamo churns within this layer of metallic hydrogen, driven by convection and the planet's rapid spin. Curiously, Saturn's magnetic field is extremely symmetrical, nearly aligned with its rotation axis. This symmetry challenges conventional dynamo theory, which expects an offset or tilt to the field. At the very center of Saturn lies a core, possibly made of rock and ice. Estimates suggest this core is about 9 to 22 times the mass of Earth, though it's not sharply defined. Recent studies suggest that instead of a solid core, Saturn may have a fuzzy core, a region where heavier elements are dissolved into the surrounding metallic hydrogen, creating a gradual transition rather than a distinct boundary. This fuzzy core idea has gained support from Cassini's gravity data and ring seismology. These methods suggest the core extends over a significant fraction of Saturn's radius, and may be more diffuse than previously believed. If true, it tells us something profound, that giant planets don't just sit quietly. Over billions of years, they mix, evolve, and redistribute their mass in ways we're only beginning to understand. Another intriguing question is, how hot is Saturn inside? Though Saturn receives sunlight like any other planet, much of its heat comes from within. Saturn radiates about 2.5 times more energy than it receives from the Sun. This internal heat is left over from formation and is sustained by processes such as helium rain. In Saturn's deep interior, helium does not mix easily with hydrogen. Instead, helium droplets form and sink toward the core, releasing gravitational energy as heat. This process, called helium differentiation, may explain why Saturn emits so much heat and why its outer atmosphere has less helium than expected. Jupiter likely experienced a similar phase earlier in its life, but Saturn, being smaller and cooler, may still be undergoing this process today. Understanding this behavior provides critical insight into the thermodynamic evolution of gas giants, not just in our solar system, but around other stars as well. Then there's the question of Saturn's density. It's the only planet in the solar system that is less dense than water, with an average density of about 0.69 grams per cubic centimetre. This means that if you could place Saturn in a bathtub large enough to hold it, it would float. Though, of course, the planet's immense gravity would crush anything that tried to do such a thing. This low density emphasizes just how gas-rich Saturn is. Despite its size, it's about 9 times wider than Earth. Much of that volume is made up of lightweight hydrogen and helium. It's a planet of scale and subtlety, where mass is wrapped in atmosphere and power is stored in silence. When scientists study Saturn's composition, they look for traces of heavier elements: carbon, nitrogen, sulfur, oxygen, to understand its origin. These metallicities tell us how much solid material the planet accreted during formation and help distinguish between formation models. So far, the data suggests Saturn is enriched in heavier elements compared to the Sun, though less so than Jupiter. This fits the idea that it formed in a region of the solar system with abundant icy material, enabling it to build a massive core and then capture gas before the nebula dispersed. Still, many questions remain. How exactly did Saturn's layers form? Why is its magnetic field so symmetrical? Is the core dissolving, or did it never solidify? How deep do its storms and jet streams go? Future missions will be needed to answer these questions, possibly with orbiters that can map the magnetic field in greater detail, probes that descend through the cloud layers, or instruments that can sample the composition of the deeper atmosphere directly. And as we await these missions, we turn again to Saturn's rings, which, as discussed earlier, serve as a seismograph for the planet itself. The tiny ripples in the rings reveal oscillations deep within Saturn, vibrations that offer clues about its internal structure. In this way, the rings are not just beautiful, they are instruments, recording the silent music of Saturn's interior. Each layer of Saturn tells a different story. The outer clouds show us chemistry in motion. The winds reveal the forces of rotation and convection. The deep hydrogen envelope speaks of pressure, temperature, and phase transitions. The core, whether solid, liquid, or diffuse, is a record of how planets grow. And together, these layers give us a picture of what gas giants are and what they can become. Saturn, like all giant planets, teaches us about planetary physics under extreme conditions. But more than that, it shows us the continuum of planetary possibilities, how nature sculpts different kinds of worlds from the same basic materials. Whether we look at exoplanets the size of Jupiter or super Saturns with oversized ring systems orbiting distant stars, we will always compare them to what we've learned here, around this golden, ringed world that's still spinning, still singing, still hiding secrets deep beneath its clouds. Saturn is not a solitary giant. Orbiting it are more than 150 moons and moonlets, ranging from massive icy worlds to irregular chunks of rock. Each one is a world unto itself, carrying unique features, histories, and in some cases, the tantalizing potential for life. Together, these moons form one of the most diverse and fascinating planetary systems in our solar system. Let's begin with Titan, Saturn's largest moon and the second largest moon in the entire solar system, after Jupiter's Ganymede. At 5,150 kilometers across, Titan is larger than the planet Mercury, but its size is only the beginning of its intrigue. Titan is the only moon in the solar system with a dense atmosphere, even thicker than Earth's. Its air is composed mostly of nitrogen, with small amounts of methane and hydrogen. This atmosphere creates a world of haze and weather, with cloud systems, winds, and seasons. Surface temperatures hover around 179 degrees Celsius, far too cold for liquid water, but not for liquid methane and ethane. Cassini and the Huygens lander revealed a landscape that echoes Earth in structure, but not in substance. Titan has lakes and seas of methane, river channels carved by hydrocarbons, and dune fields made of icy grains and organic particles. Mountains, valleys, and potential cryovolcanoes all suggest a dynamic geology, despite the freezing temperatures. Beneath its icy crust, Titan likely hides a subsurface ocean of liquid water, possibly sandwiched between layers of ice. This ocean, combined with the rich organic chemistry in the atmosphere, makes Titan one of the most promising places to study prebiotic chemistry, and perhaps one day even biology. That's why NASA's upcoming Dragonfly mission, a drone-like rotorcraft set to launch in the 2030s, is so important. Dragonfly will fly from one region of Titan to another, sampling the surface, analyzing complex organic molecules, and looking for the chemical fingerprints of life. But Titan is only one part of Saturn's moon family. The next most compelling is Enceladus. Although much smaller, just 500 kilometers wide, Enceladus has drawn enormous attention because of one extraordinary feature: cryovolcanic geysers erupting from its south pole. These geysers spray water vapor, ice particles, salts, and organic compounds into space, feeding Saturn's E-ring and creating a direct connection between the moon's interior and the space environment. Cassini flew through these plumes multiple times and found evidence of a salty ocean beneath the icy crust, as well as hydrothermal activity, warm water interacting with rock. This combination, liquid water, energy sources, and organic materials, makes Enceladus one of the best candidates for life beyond Earth. If microbial life exists in the solar system outside our own planet, Enceladus is near the top of the list of where it might be found. The plumes offer a rare opportunity. Instead of drilling into a subsurface ocean, we can sample the ocean directly from space. Future missions could return to Enceladus with more advanced instruments to detect biomolecules, lipids, amino acids, or even microbial cells, if they are present. Other moons of Saturn reveal different types of stories. Mimas, often called the Death Star moon, due to its enormous Herschel crater, appears heavily cratered and inactive. For years, it was considered geologically dead, but recent observations suggest Mimas may actually have a liquid ocean beneath its surface, hiding quietly under a thick, icy shell. If confirmed, this would radically shift our understanding of what moons might harbour subsurface water, even ones that appear inert from the outside. Tethys, Dione, and Rhea are medium-sized icy moons, each with unique features. Tethys has a giant canyon system, Ithaca Chasma, stretching over 2,000 kilometers. Dione shows signs of resurfacing and possible cryovolcanism. Rhea, the second largest of Saturn's moons, may have thin rings of its own, something no other moon in the solar system possesses. Iapetus is one of the strangest moons in the entire solar system. It has a stark two-tone coloration. One hemisphere is bright as snow, the other as dark as coal. It also has a massive equatorial ridge, rising 20 kilometers high and circling much of the moon like a seam. The cause of this ridge remains unclear, though it may be the remnants of an ancient ring that collapsed onto the surface. Then there's Hyperion, a sponge-like moon that tumbles chaotically as it orbits Saturn. Its surface is full of deep, dark craters and porous ice, making it one of the least dense moons known. Its rotation is unpredictable, changing over time due to interactions with nearby moons, and it looks more like an asteroid than a typical spherical moon. Phoebe, one of Saturn's outermost moons, is another oddity. It orbits Saturn in a retrograde direction, opposite the planet's rotation, and its orbit is highly inclined. This suggests that Phoebe was captured, perhaps from the Kuiper belt, and brought into Saturn's domain. It's a reminder that Saturn's gravitational influence reaches far into space, capable of seizing passing objects and adding them to its family. Many of Saturn's smaller moons serve as shepherds for the rings. Prometheus and Pandora can find the F ring, creating intricate braided patterns. Pan and Daphnis, orbiting within ring gaps, stir up waves that ripple through the ring material. Their gravitational interactions are small but precise, maintaining the structure of the rings like invisible gardeners tending a cosmic garden. In total, Saturn's moons form a kind of planetary system within a planetary system. There are large moons like Titan and Rhea, mid-sized moons with varied geologies, irregular moons in distant, inclined orbits, and moonlets embedded in the rings. Some formed with Saturn, others were likely captured. Some are active, others dormant. Some may be slowly disintegrating, while others are still growing. Together, they reflect the complexity and diversity of Saturn itself. They offer clues about how moons form, how planetary systems evolve, and how conditions for life may arise in the most unexpected places. Saturn's moons also provide a window into the past. Crater counts allow scientists to estimate surface ages. Tectonic features record stresses from tidal forces. Plumes and geysers reveal active processes today, and chemical analysis of surface materials, particularly organics, helps reconstruct the solar system's early chemistry. But the moons do more than inform. They inspire. Each new image from Cassini, each spectrograph reading, each gravitational anomaly told a story we hadn't heard before. An ocean under ice, a nitrogen haze, a methane lake, a ridge circling a moon, a geyser of salty vapor. These are the wonders that Saturn's moons offer us, and there is still so much we don't know. Future missions may carry more advanced tools, penetrating radar, ice drills, chemical laboratories, seismometers, or even submarine probes for alien oceans. As we send machines farther and make them smarter, our ability to explore these distant moons will only grow. And each time we land, fly by, or orbit one of Saturn's moons, we return not just with data, but with perspective. We see how varied a planetary system can be. We see how different conditions create different geologies, chemistries, and possibilities. And we realize how rare and fragile life is, and how deeply it connects us to these far-off worlds. Saturn's moons are not mere satellites. They are companions in orbit, storytellers of formation, timekeepers of solar system history, and perhaps harbingers of something more. Something alive, something waiting to be found. As we conclude our journey through Saturn's story, we find ourselves looking back over billions of years and countless mysteries, each piece woven into the rich tapestry of this ringed giant's life. Saturn is a world of contrasts, majestic yet delicate, ancient yet active, distant yet intimately connected to the Earth through the shared history of our solar system. Its rings shimmer with icy particles that may be as young as a few 100 million years, while its core has held its secrets since the dawn of time. Its moons range from barren ice balls to dynamic worlds with oceans, atmospheres, and chemical gardens. Our exploration of Saturn has been a story of human curiosity and ingenuity. From Galileo's first fuzzy observations through the telescopes of the 17th century, to the detailed, breathtaking images and data from the Cassini-Huygens mission, each step has expanded our understanding and deepened our wonder. The questions we ask about Saturn go beyond science. They touch on our place in the universe and the search for life beyond Earth. Titan's thick atmosphere and lakes of liquid methane, Enceladus's erupting geysers and hidden ocean, the complex chemistry of the rings and atmosphere, all hint at a world that is alive with possibility, even if life itself remains undiscovered. Saturn teaches us about planetary formation and evolution, about the forces that shape worlds, and about the delicate balance of celestial mechanics. Its storms remind us of the power of nature. Its rings speak of beauty born from destruction, and its moons whisper stories of origins and change. As we drift asleep under the gentle light of distant stars, Saturn remains a silent guardian in the night sky, a cosmic sentinel watching over our small blue planet. The light that reaches us from Saturn takes more than an hour to arrive, carrying with it tales from a world that is at once foreign and familiar. When you gaze up at the night sky, imagine the swirling bands of Saturn's clouds, the glittering rings casting shadows across a giant world, and the icy moons orbiting silently in the darkness. They remind us that the universe is vast, filled with wonders yet to be explored. In the quiet moments before sleep, let the knowledge of Saturn's grandeur soothe your mind. Its steady orbit, its rhythmic storms, and its intricate moons offer a cosmic lullaby. Proof that even in the vastness of space, order and beauty endure.
Thank you for joining this journey into Saturn's story. May the mysteries of the ringed giant inspire your dreams and curiosity, inviting you to look upward, to wonder, and to keep exploring.
Good night, and may your rest be as deep and peaceful as the vastness of space itself.